This is a Fortigate-based ADVPN demonstration. In this demonstration, we have two hub sites, HUB1 and HUB2, and we've got two branches, branch 2 and branch 3. In this setup, obviously we have two hubs. The hubs themselves are our VPN orchestrators. Technically, you only need one, but for redundancy reasons, if you were to lose a hub, you wanted to make sure you have a redundant hub to be your VPN orchestrator. All of the sites have two internet connections or two circuits. WAN 1 simulates a fast path, being a fiber or MPLS or E-line or private line, and WAN 2 being a little higher latency a cable, sort of a DSL backup. As far as the overlays, we have 4 total overlays. We have 2 overlays going to HUB1 and 2 overlays going to HUB2, as we're using all of the circuits we have. For our first test, we'll be doing a branch to hub test, and that's simply communicating from this host down here, 2.2.2.1 up to 1.1.1.1. So let's go ahead and get a ping started here. So let's simply do a ping 1.1.1.1, and we see the traffic traversing. Let's go look at branch 2 here and look at our VPN tunnels. So right now we only have 4 VPN tunnels. That is expected, right? Each one of those VPN tunnels is our overlay. We have 2 overlays to HUB1 and 2 overlays to HUB2. ADVPN, the AD in ADVPN stands for Auto Discovery VPN. So you only need to have VPN tunnels to your hubs, and then the hub will dynamically, broker or show you how to create a dynamic tunnel between your different branches. So let's see how this is all working. If we go look at our SD-WAN configuration, we see we have a performance SLA. The performance SLA is checking the path across those different circuits up to HUB1 and up to HUB2. So specifically, if we look at HUB1, we have a server at HUB1, 100, 100, 100, 100, which just happens to be a loopback address within HUB1. And we're doing a ICMP, we're doing a ping to that host or that IP address, and we're checking the latency. If the latency is below 120 milliseconds, we're within SLA. If it's above 120 milliseconds, we've fallen out of SLA. And we're checking every 500 milliseconds, so every half second. And if there's 5 failures, we'll switch our path and we'll restore after 5. So the way the performance SLA works is that it is called out in an SD-WAN role. So if we look at our SD-WAN role here, this rule number 1 here, we see that for rule number 1, we're going to use path number 1 if we're within SLA. If we fall out of SLA, this checkbox should drop down to path 2, and we should use path 2. So let's go ahead and test this out. So if we look at our connection right now, let's do a quick packet capture. We see that our packets going to 1.1.1.1 are using HUB1 path 1. And like I said, if the latency goes above 120 milliseconds, we should switch over to path 2. So let's go ahead and add some latency in here. Let's add 222, which is bidirectionally, it's 444, 445. So right now, the Fortigate's doing its constant every half second test, and it just realized that, hey, that's above right here. This 445 is above 120 milliseconds. We need to get out of this path and get on our secondary path. And sure enough, we're using HUB1 path 2. We go back to our performance SLA. We can see that we're out of SLA on this path. So based on that SLA, we're going to pull out path 1 and not use it anymore and use path number 2. So there we go. Now let's go ahead and normalize that connection and see what happens. What we expect to happen is that performance SLA, since we just dropped the latency back down to 2 milliseconds, 4 milliseconds, that performance SLA should realize, hey, path 1 is back in action. It's doing really well. Let's revert back to that path. And sure enough, we reverted that path. And as we can see here in our packet capture that's currently live, we're back to HUB1 path number 1. Our performance SLA, let me refresh the screen here. Our performance SLA still says it's back in SLA. It's about 5 milliseconds, and our SD-WAN rule is back to path number 1. So that satisfies the branch to hub communication, failover, failback. Now let's talk about branch to branch communication. And to do so, let's bring up a packet capture here as well. And let's stop this packet capture and let's change it over to the branch 3 hosts as well. And you may ask, why am I doing a packet capture on the hub? And here's the reason. If we go back to our IPsec monitor here, we see we only have 4 VPN tunnels, like we should. Those are our 4 overlays. That the very first packet we send from branch 2 to branch 3 goes up to our hub. Our hub then brokers the connection and tells branch 2 and branch 3 how to communicate directly. In technical terms, it sends a shortcut query up to the hub, and the hub then sends a shortcut response telling the two how to connect to each other. So if we watch this in real time, what we expect is that very first packet to come up to hub 1, and then all the packets after that to go direct between the 2 sites. Let's do a ping 3.3.3.1 -t. And sure enough, look at here on our hub, we see that very first set of packets come in to the hub and back down, and then the hub negotiates that direct shortcut tunnel, that path between the 2, and no more traffic goes to the hub. It's now direct site to site. And we can see it here, hub1 path 1 _0. That underscore signifies a shortcut tunnel. If we come back to our IPsec monitor and we refresh the screen, we can see we now have a 5th tunnel. That 5th tunnel is our shortcut path directly over to branch 3. So let's do what we did before. Let's introduce latency. So we're going to introduce some latency there. We see it pop up. Let's go to our SD-WAN, our performance LAN, and it dynamically picks up that shortcut tunnel and now realizes that it's outside of our latency. Let me refresh it to get the real numbers. It's 444 milliseconds. It's outside of the latency, and this should push us over to the secondary circuit, just like it did. We see a checkbox here, and just like we saw, we had our high latency. The Fortigate realized it, and it pushed us across our secondary circuit, which is roughly about 22, 23 milliseconds. So let's revert that back. And again, the Fortigate should realize, hey, we're coming back into SLA. We're sub that 120 milliseconds, and it should revert that path back to the fast path, that 4 or 5 millisecond path here shortly. And sure enough, we revert back, and looking at our packet capture, we're back here to our primary path. I'm going to go ahead and stop this, and let's scroll up so we can show you that we actually did go across our path 2 _0, so our shortcut path. And if we look at our VPN tunnels, we should have a total of 6 now. Refresh this, and we have a total of 6. We've got our shortcut tunnel across path 1, and then we've got our shortcut tunnel across path number 2. Obviously, since we reverted back, we're now traversing hub1 path 1 _0, which is our shortcut path. And that's also shown like we were just showing in our packet capture here. And there we go. So that satisfies the branch to branch traffic. So let's talk about what happens in a failure scenario where we lose an internet connection. And I think the best way to do that is on branch 2. Let's just kill WAN 1. So let's go to our network interfaces and simply click on WAN 1, and let's disable it. This is basically simulating that we just lost WAN 1. You see we lost a few packets, and Fortigate realizes that circuit's down, and we go over our path 2 shortcut tunnel, and we see that right here. Now let's revert that back. Let's bring back this connection. Now, when we bring it back, it's going to take a little bit longer. There's a few things that need to happen in the background. 1, the interface needs to come up. 2, the IPsec tunnel back to the hub needs to come back online. And then 3, BGP peering needs to happen, and the prefixes between the sites need to share. So we see that take usually about 25 to 30 seconds. So in about 25 to 30 seconds, all of that should happen. And the Fortigate should realize that, hey, path 1 is back online, and that's the faster path. Let's go ahead and use it. And sure enough, we see that happen right here, the transition from 22 milliseconds back down to our fast path. So there we go. We've just shown test number 3 with the ISP failure. So let's talk about hub failure. Again, the hub is our VPN orchestrator. Without our VPN orchestrator, there's no way for us to auto-discover our peers or the fellow branches, the fellow spokes. So if we were to lose a hub, we wouldn't be able to communicate with each other. Obviously, this can be set up with a single hub, but if you lost that single hub, we couldn't communicate to each other. But if you're in a environment with just a data center, and if your data center's down, you're dead anyway, there may not be a reason to have a second hub. But then again, if you ever do maintenance, you kind of want a second hub if you ever do for redundancy, if you ever do maintenance on that primary hub. So in this scenario, let's get a packet capture going on hub number 2. We still got this packet capture going on hub 1, but what we're going to do, and let's look at our IPsec tunnels. We still should have our 6 IPsec tunnels. And notice if a shortcut tunnel is not used after 15 minutes, I believe that's the default, it will actually disconnect. It'll disappear. So if it's not being used, the idle timeout's about 15 minutes, and it'll disappear. What we expect to happen if we shut down hub 1 is we should be seeing some shortcut paths coming across hub number 2. So let's go ahead to hub number 1, and we are basically going to simulate this thing completely dying. So we're going to shut down WAN 1 and WAN 2. So this thing is basically theoretically dead. Now it's still using that hub 1 path 1 until right there. We just saw it. I'm going to stop it there. It was still using hub 1 path 1 for a short time until it realized, hey, my hub is gone. I lost those BGP paths from hub 1, and it quickly switches over to hub 1 path 20. And then it realizes, hey, that's dead as well, because that's hub 1. And we can see it actually switched over to hub 2 path 1. So you can actually see that happen right here. You can see it's going over the primary shortcut tunnel on path 1. Then it says, hey, that's dead. And then it quickly goes over to the shortcut tunnel on path 1 and says, hey, that's dead too. We lost a single packet. And now it's going across the hub 2 path 1. And the reason we see just a slight amount of packets on the hub 2 is, again, that very first packet comes up to hub 2 and it says, hey, how do I communicate with my partner over here, my fellow branch? And it gets that shortcut offer, and then has that direct communication. So if we refresh the screen here, we should see that shortcut tunnel across, the shortcut tunnel across hub 2 path 1 right there. And again, just to be thorough, we're going to do like what we did before. We're going to add some latency on here. And we would expect latency here, and then we should see it fail over to the connection over here and right here, just like we saw in hub 2. That shortcut tunnel offer going across path number 2 is offered up there. And if we refresh the screen, we should see a hub 2 path 2 _0. And sure enough, hub 2 path 2 _0. And Fortigate's finally realized that hub 1 is completely dead. If you remember, we shut down everything on hub 1. So everything's going across hub 2. So let's normalize this configuration on hub number 2. So the traffic goes back across a fast path. So once that's normalized and we're back down to our 5 milliseconds, then we will bring back, we'll bring hub 1 back alive and see what it looks like when it reverts back. Okay, so we're back on our path. Let's go look at our SD-WAN rule. You can see hub 1 is completely dead. It's just bright red, and we're using hub 2 path 1. If we look at our performance SLAs, hub 1 is completely dead. So let's bring hub 1 back alive, fully alive. Enable WAN 1, enable WAN 2. And again, like I said, circuit needs to come up, IPsec needs to establish, the BGP routing protocol needs to peer, the prefixes need to be shared. before it realizes, before it takes that path again. So it's looking at our packet capture here, right? And that's going to take about 30 seconds. We're still using HUB2 path 1. We expect that to revert back to HUB1, as HUB1 is our primary orchestrator, VPN orchestrator in our configuration here. Give that a few seconds. As the Fortigate realizes that BGP's up, and then those SLAs are back within SLA. And there it is. It just took a little longer. My environment here is running on an ESXi server. All of these are Fortigate virtual machines with 1 gig of memory. So things are slightly slower sometimes. Either way, we're back on HUB1 path 1, just as expected, and using that shortcut tunnel. So the environment is back to normal. We have HUB1 up, HUB2 up, and we're normalized, with our latencies and stuff. So that covers test number 4. So let's talk about actually application steering. And let's do, for application steering, what is application steering? It's basically a glorified policy route. If we look at our actually, let me go ahead and just delete this one. We're just going to start over here. If we create a new SD-WAN rule, which is a glorified policy route, let's say, for example, we have an application at the data center. Let's call it our backup server. We don't want our backup traffic to traverse WAN 1, which is all of our, all the other users and corporate users. We don't want to affect them with backup traffic. We want backup traffic to go across WAN number 2. So let's call this backup. And let's say the source is the 2 network. And then let's say the destination is the backup server, host 1.1.1.1. And in this scenario for our testing, we're just going to do ICMP, and we're going to use the best quality. So the interface with the best measured performance is selected. So the interface preference, if there's a tie, it's going to be path 1 and then path 2. And the measured SLA is going to be HUB1, and the quality is latency. So we're going to hit OK here. Now, note when you create a new SD-WAN rule, it pops it in the bottom of the list. So we're going to want to drag it up to the top. So what have we done here? We just said that any traffic going over to 1.1.1.1 is going to use the best path based on latency. So let's ping 1.1.1.1. Okay. Right, it's going to use the path with the lowest latency. If we look at our performance SLA, the latency across path 1 is 4 milliseconds, and the latency across path number 2 is 22 milliseconds. So if we bump path number 1 above 22 milliseconds, we should see it go over path number 2. Now, if you remember, our performance SLA is 120 milliseconds, but that is for our other SD-WAN rule. So what we're going to do now is divert the traffic, if that makes sense. And we'll showcase it. We'll show that right here. So if we get this above, let's change this to 66 milliseconds. We see it pop up over 66 milliseconds, but 66 milliseconds is not the fastest path. The fastest path is the one with the lowest latency, which is the 23 millisecond path. So if we come over here to our SD-WAN rule, we should see that traffic to our server is now taking path 2, but traffic to all other sites are taking path 1 because path 1 is still below the 120 millisecond SLA threshold. So you can see that this rule here is using an SLA threshold. This rule here is using the best path with the lowest latency. And that's basically how application steering works in a nutshell. You can use latency, you can use jitter, you can use packet loss. Additionally, you don't have to have an address. You can use the internet service. You can say, all of Microsoft Azure. You can have an application steering rule for that. If you have application inspection turn on, where it's actually inspecting your packets and seeing what the application is, you can do Zoom calls. You can say, hey, all Zoom calls go over the secondary path or go over the primary path. So that is application steering, in a nutshell there. So let's normalize everything, and now let's discuss how all of this works. I'm going to try to make this as simple as possible, but we're using BGP. And obviously, the way it works from an SD-WAN perspective is we have an SLA, and based on the SD-WAN rule, it checks that SLA, and the traffic that is within that SLA goes across path 1. And if the traffic is, if the SLA is outside of SLA, it goes across path number 2. That's great for outbound traffic. But how do we communicate that our path is dirty or bad to the hubs? Well, that's done with BGP. So if we look at BGP and we look at our BGP neighbor relationships, obviously we have 4, as we have 4 tunnels. We have these 2 route maps. We have a route map preferable and a route map fail. So we go look at those route maps. The route map preferable, which is the route map path 2 on that one, path 1 here, that sets the community, right? Sets the community as 65,000:1, 65,000:2, or 65,000:666. That's great, but what that does is that tags the BGP traffic with a community string, and that community string gets sent up to the hub, and then the hub makes routing decisions based on that community string. That's great, but how do we change between preferable and standard or non-preferable? Well, we use SD-WAN. So if we do config system SD-WAN, we do show, and we scroll down to our neighbor section, we can see each one of these neighbors is a BGP peer. So what we're using on this BGP peer within SD-WAN is a health check against HUB1. So if we're within SLA, like we're below that 120-second threshold, then we will use the preferred route map. As soon as we fall outside of SLA, we use the route map fail, which is the community string is 666. So let's go over to a hub and see what the hub's doing, right? Because the hub needs to interpret the traffic and say, hey, your WAN 1 traffic is, your WAN 1 path is dirty. I'm going to send traffic across your better path. We do config router BGP and look at the configuration there. We have a route map in, it says route map route tag. If we take a look at that, we see that the route map route tag matches a community and then sets a route tag. So let's look at the community. So here is our community. So if the community list, our community string 65,000:1 comes in, we're going to set our community to C path 1. And when we set it to C path 1, we're going to set our route tag to path 1. And the same for path 2 and the same for route tag 666. So the traffic, the BGP route comes in, it has a community string on there. That community string gets evaluated, and then we apply a route tag. And then on the hub, if we go look at our SD-WAN configuration, in the SD-WAN rules on the hub, we could see we base all of our SD-WAN rules based on a route tag. So if you match route tag 1, you use path 1. If you match route tag 2, you use path number 2. And in a failure scenario where both circuits are out of SLA, we need some sort of catch-all, and we just prefer path number 1. Now, additionally, we have a policy route. And the policy route says if traffic comes in over path 1, go out of path 1. And if traffic comes in path 2, go out of path 2. and that makes sure we have a symmetric path, that we're not using asymmetric routing to do some cross overlay traffic. That is SD-WAN with Fortigate in a nutshell. I hope I covered everything that really needs to be covered with failover, failback, and actually how it's actually working with the BGP protocol. Please let me know if you have any questions. Thank you.